Hello, my dear students. Welcome to IKSR chemistry classes. In this video, we will discuss an interesting topic in the spectral properties of transition metal complexes, and it is charge transfer spectra. Two common types of electronic transitions in transition metal complexes are DD transition and charge transfer transition. Let us see what are these. The electronic transitions in transition metal complexes in which the electron moves from one d atomic orbital to another d atomic orbital are called DD transitions. The electronic transitions in transition metal complexes in which the electron moves from one d atomic orbital to another d atomic orbital are called DD transitions. While the electronic transitions in which the electron moves from an orbital which is localized mainly on the ligands to another orbital which is localized mainly on the metal atom or vice versa are called charge transfer transitions, and the spectra obtained in this way are called charge transfer spectra. Let us see it again. The electronic transitions in which the electrons moves from one orbital which is localized mainly on the ligands to another orbital which is localized mainly on the metal atom or vice versa are called charge transfer transitions, and the spectra obtained in this way are called charge transfer spectra. Features of charge transfer transitions and charge transfer spectra. The charge transfer transitions require greater amount of energy than DD transitions, and therefore the charge transfer spectra are generally obtained in the blue end of the visible spectrum and often in the UV region also. It is a noteworthy fact that the charge transfer transitions require greater amount of energy than DD transitions, and this is why charge transfer spectra are generally obtained in the high energy end of the UV visible spectrum, that is in the blue end of the visible spectrum or in the UV region. The charge transfer transitions are fully allowed according to selection rules. It means the charge transfer transitions involve G-ray, unG-rayed orbitals and delta S equals to 0. This is why charge transfer bands are strong and their molar extinction coefficient is high, often in the range 10 to the power 3 to 10 to the power 4. As a result, the color of a compound arising from charge transfer transition has high intensity. In nutshell, we can say that charge transfer transitions are fully allowed according to selection rules, and they are highly probable. Their probability is high, and therefore the charge transfer bands are strong and their molar extinction coefficients are high, often in the range 10 to the power 3 to 10 to the power 4, and the color of a compound arising from charge transfer transition has high intensity. Types of charge transfer transitions. The charge transfer transitions are of three types as mentioned below. Ligand to metal charge transfer, LMCT. Metal to ligand charge transfer, MLCT. And metal to metal charge transfer, MMCT. These are the abbreviations. There are three types of charge transfer transitions: ligand to metal, metal to ligand, and metal to metal. First of all, we will see ligand to metal charge transfer. Ligand to metal charge transfer. This type of charge transfer transition takes place in hexahalo or tetraoxo complexes of transition metals. Hexahalo and tetraoxo complexes of transition metals exhibit LMCT, the halide ion, that is X minus ion, or oxide ion, that is O2 minus ion, it should be 2 minus, contain filled pi orbitals. The halide ions, that is X minus, or oxide ions, that is O2 minus, contain filled pi orbitals. These pi electrons can undergo transition to vacant anti-bonding MOs, which are localized mainly on the metal atom or ion. Thus, it is called ligand to metal charge transfer. Let us see it again. Ligand to metal charge transfer transition takes place in hexahalo or tetraoxo complexes of transition metals. Halide ion or oxide ion contains filled pi orbitals. These electrons can undergo transition to vacant pi bonding MOs, which are localized mainly on the metal atom, and therefore this type of electronic transition is called ligand to metal charge transfer. The partial MO diagram for hexahalo complexes is given below. This is the partial molecular orbital diagram for hexahalo complexes, in which there are 6 X minus ions as ligand. These are ligand sigma orbitals, these are ligand pi orbitals, and these are the mainly d atomic orbitals of the metal, which are symbolized as T2G and Eg. This is pi star, it is sigma star MO. It means these are anti-bonding MOs, which are localized mainly on the metal atom, while these are the bonding MOs, which are localized mainly on the ligands. 4 types of transitions are possible. These bonding MOs are completely filled by electrons, and these electrons are provided by ligands. These electrons present in molecular orbitals, which are localized mainly on the ligands, can undergo transition to vacant anti-bonding MOs, which are localized mainly on the metal atom. And this type of electronic transition is called ligand to metal charge transfer. These 4 transitions, pi bonding to pi anti-bonding, is abbreviated as nu1. Pi bonding to sigma anti-bonding, it is abbreviated as nu2. Sigma bonding to pi anti-bonding charge transfer is abbreviated as nu3, and sigma bonding to sigma anti-bonding is abbreviated as nu4. It must be noted that this transition requires the maximum amount of energy. Maximum amount of energy is required for the electronic transition nu4, and all these electronic transitions involve the transfer of electron from orbitals which are localized mainly on the ligand to orbitals which are localized mainly on the metal atom, and hence these electronic transitions are called ligand to metal charge transfer transitions. Four electronic transitions are possible as shown in the above diagram and illustrated in the following table. New one requires the minimum energy RuCl3 3 minus, RuCl6 3 minus, RuCl6 2 minus, and OSCl6 3 minus. All these are hexahalo complexes, and these complexes exhibit new-one absorption peak. This absorption peak is sharp and intense, but these are not obtained in the case of D6, because in the case of D6 transition metal complexes, these pi star MOs are completely filled. In the case of D6 transition metal complexes, T2G set of orbitals, that is pi star MOs, are completely filled, and hence this electronic transition is not possible in the case of D6 transition metal complexes containing 6x minus ions. These complexes exhibit new-one absorption peak. This absorption peak is sharp and intense, but it is not obtained in the case of hexahalo complexes of D6 transition ions. Nu2 is exhibited by PTBr6 2 minus, PTI6 2 minus, and all of the above complexes. This absorption peak is narrow, and it is of lowest energy in the case of D6, because in the case of D6 nu1 is not observed. Another absorption peak nu3 is broad and weak, and it is generally not observed, and hence no example of this type of charge transfer transition is available. Nu4, these transition metal complexes PTBr6 2 minus, PTI6 2 minus, and OSI6 2 minus exhibit Nu4 type of absorption band observed in certain cases, such as in the case of these complexes, but this transition requires the maximum amount of energy, and it is generally beyond the range of observation. Please note that all these are hexahalo complexes. In all these complexes, the transition metal ion is surrounded by 6 halide ions. Metal to ligand charge transfer. This type of charge transfer transition is expected. Metal to ligand charge transfer transition is expected when the ligands possess low-lying empty orbitals. The ligands have low-lying empty orbitals, and the metal has filled orbitals having energy greater than highest energy filled ligand orbitals. There must be two conditions for metal to ligand charge transfer. The ligands should have low-lying empty orbitals which can accept the electron coming from metal, and at the same time metal ion has filled orbitals, and these filled orbitals have energy greater than the highest filled ligand orbitals. Otherwise, ligand to ligand charge transfer will take place. The best examples of this type are provided by complexes containing CO, CN-, aromatic amines, etc. These ligands contain vacant pi star MO, and in these MOs, the electrons provided by metal can be accommodated. In the case of octahedral metal carbonyls, such as CrCO6 and MoCO6, pairs of intense absorption bands have been assigned to transitions from bonding, which are localized mainly on the metal, to anti-bonding, which are localized mainly on the ligand component of the metal ligand pi bonding interaction. It means these hexa metal carbonyls, that is octahedral metal carbonyls, exhibit pairs of intense absorption bands due to metal to CO pi bonding. In this pi bonding, the electron is transferred from metal atom to vacant pi star MO of the ligand. And due to these transitions, CrCO6 and MoCO6 exhibit pair of intense absorption bands. The UV visible spectrum of NiCN whole 4 2 minus. This is a square planar complex compound, and its UV visible spectrum consists of three medium to strong absorption bands at 32,000, 35,200 and 37,600 centimeter inverse. These absorption bands have been assigned to transitions arising from filled d atomic orbitals of the metal ion to the lowest energy orbital formed from pi star orbitals of the set of 4 Cn- ion ligands as illustrated in the following diagram. There are 4 Cn- ions in this complex, and each Cn- ion has pi star orbitals. These pi star orbitals of 4 Cn- ion take part in linear combination producing pi star orbitals of the ligands, and the electrons of Ni2 plus ion undergo transition from d atomic orbitals to these vacant pi star orbitals of Cn- ions. Thus, this type of electronic transition is called metal to ligand charge transfer, and it has been illustrated in the following figure. These are pi star ligand group orbitals, which are produced by the linear combination of pi star MOs of 4 Cn- ions, which are present in the complex compound under consideration NiCN whole 4 2 minus. These are the pi star ligand group orbitals of 4 Cn- ions, and these are vacant. The splitting of Ni2 plus ion in a square planar crystal field is given here. NiCN whole 4 2 minus is a square planar complex compound, and a splitting of d orbitals is as follows. dxz, dyz orbitals are completely filled, dz square orbital is also filled, and dxy orbital is filled, while dx2 minus by 2 orbital is vacant. Now, three types of transitions are possible from filled d atomic orbitals of Ni2 plus ion to vacant pi star ligand group orbitals of 4 Cn- ions, and these are represented here. dxy2 pi star ligand group orbitals, and this transition requires minimum amount of energy, and hence its wave number is lowest, 32,000 centimeter inverse. While this transition from dz square orbital to vacant pi star ligand group orbitals requires greater amount of energy, and its wave number is higher. 35,200 centimeter inverse, while the transition from dxz or d by z atomic orbital of Ni2 plus to vacant pi star ligand group orbitals requires the maximum amount of energy, and therefore the wave number of this absorption peak is the highest, 37,600 centimeter inverse. All these charge transfer transitions involve the transition of electron from filled d atomic orbital of metal to vacant pi star ligand group orbitals of the ligand, and hence this type of electronic transition is called metal to ligand charge transfer transition. And now third type of charge transfer transition is metal to metal charge transfer, MMCT. The intense blue color of Prussian blue. The name is itself indicating that its color should be blue. The intense blue color of Prussian blue arises due to Fe2 plus to Fe3 plus, that is metal to metal charge transfer via the bridging cyanide ion. Prussian blue has intense blue color, and this color arises due to Fe2 plus to Fe3 plus electron transfer, that is metal to metal transfer via the bridging cyanide ion. First of all, the electron is transferred from Fe2 plus ion to cyanide ion. This electron transfer takes place, and then the electron is transferred from cyanide ion to Fe triple plus. Thus, Fe2 plus to Fe3 plus metal to metal charge transfer takes place via the bridging cyanide ion. Here Cn minus ion acts as a bridging ligand. It is attached to Fe2 plus ion through carbon atom, while Fe3 plus ion through nitrogen atom. It is Prussian blue having intense blue color. The pi bonding system of Cn minus ion. Cn minus ion has pi bonding system, which facilitates the transfer of electron from Fe2 plus to Fe triple plus. Colors of some other compounds arising from charge transfer. This is potassium dichromate having intense orange color. The deep orange color of potassium dichromate having chromium in +6 oxidation state with 3d0 electronic configuration arises due to it has no electron in the d orbital, and its color arises due to oxide ion to chromium 6 plus charge transfer. DD transition is not possible in this complex because its electronic configuration is 3d0, and hence its color arises from oxide ion to chromium 6 charge transfer. It is potassium chromate having intense yellow color. The deep yellow color of potassium chromate having chromium in +6 oxidation state with 3d0 electronic configuration again arises due to oxide ion to Cr6 plus charge transfer, and it is potassium permanganate which has intense purple color. Its intensity of color is so high that it appears almost blackish. It is potassium permanganate. The deep purple color of potassium permanganate having Mn in +7 oxidation state with 3d0 electronic configuration arises due to oxide ion to Mn7 plus charge transfer. It must be noted that the intensity of color of a compound arising from charge transfer transition is much higher than that arising due to DD transition. Now the time for self-assessment. KMNO4 is intensely violet or purple colored, but KTCO4 and KREO4 are colorless. Similar compounds Mn, manganese, technetium, rhenium belong to the same group 7 of the periodic table, and the compounds are similar. KMNO4 has intense purple or violet colored, while these compounds are colorless. We have to explain the reason behind it. Here is the answer. The intense purple color of KMNO4 arises due to oxide ion to Mn7 plus charge transfer, which absorbs electromagnetic radiation from the visible region. KTCO4 and KREO4 also undergo oxide ion to Tc7 plus and oxide ion to Re7 plus charge transfer transitions respectively. But these transitions lead to absorption of ultraviolet light rather than visible light. These compounds also exhibit charge transfer transitions, but these transitions absorb UV light and not visible light. Any compound is colored only when it absorbs light from the visible region of electromagnetic radiation, but these compounds absorb UV light and hence these are colorless. On similar grounds, K2CrO4, that is potassium chromate, is intensely yellow colored, but similar compounds potassium molybdate and potassium tungstate are colorless on the similar grounds. Now the time for another self-assessment. Write down names of KTCO4 and KREO4. These compounds are similar to KMNO4, having name potassium permanganate, and hence their names should be potassium pertechnetate and potassium perrhenate. Now the time for another self-assessment. KMNO4 exhibits two absorption bands. KMNO4 exhibits two absorption bands at 18,500 centimeter inverse and 32,200 centimeter inverse due to ligand to metal charge transfer. Estimate the value of delta T for MnO4 minus ion. This is the question which is to be solved. KMnO4 exhibits two absorption bands at 18,500 centimeter inverse and 32,200 centimeter inverse, and these transitions are due to ligand to metal charge transfer. Then we have to calculate the value of delta T for permanganate ion. It is the solution. There is tetrahedral arrangement of 4 oxide ions around Mn7 plus ion in MnO4 minus ion. In permanganate ion, Mn7 plus ion is tetrahedrally surrounded by 4 oxide ions, and its color arises due to oxide ion to Mn7 plus, that is ligand to metal charge transfer. Its partial MO diagram and the probable ligand to metal charge transfer transitions are given here. T2, A1, E and T2. These orbitals are bonding in nature and these are filled by the electrons of oxide ion, while these orbitals are anti-bonding in nature, which are localized mainly on the Mn7 plus ion, while these bonding MOs are localized mainly on oxide ion, and hence this electronic transition is called oxide ion to Mn7 plus charge transfer transition. Due two transitions are possible, A1 to E and T2 to T2. These are anti-bonding MOs while these are bonding MOs. These are anti-bonding and these are bonding. This transition requires 18,500 centimeter inverse while this transition requires 32,200 centimeter inverse. And it is obvious that the difference between these two wave numbers should be equal to this one. The difference between this transition and this transition is equal to this one, delta T. It is obvious that delta T is equal to 32,200 centimeter inverse minus 18,500 centimeter inverse, and the net result is 13,700 centimeter inverse. Thus, the crystal field splitting energy in MnO4 minus ion, that is delta T, is 13,700 centimeter inverse. Thank you for watching the video with patience.